Hello, my name is Sergei Slizovsky, and I'm going to talk about Brown-Zak oscillations explained by Aharonov-Bohm effect for the network of critical trajectories near Lifshitz transition. It is based on the joint work of a theory group from Manchester and experimental group of Klaus Enslin from ETH. Experimental observation of Brown-Zak oscillations was pioneered in Manchester. In graphene aligned with hexagonal boron nitride, high-temperature oscillations of conductance were observed. These were periodic in inverse magnetic field and had maxima at integer fractions of magnetic flux per Mohr unit cell. The conductance maxima can be ascribed to the appearance of the Brown-Zak fermions, the effective quasi-particles constructed on extended magnetic unit cell that already incorporate the effect of magnetic flux in them, and so propagate ballistically feeling no magnetic field. Currently, Brown-Zak oscillations are observed in many different Mohr heterostructures. Theoretically, the Brown-Zak oscillations were first predicted in the work of Mark Asbel, even before the works of Brown and Zak. It was understood already in 1960s that Brown-Zak oscillations can be explained both from the point of view of the exact spectrum and from the semi-classical approach combined with the magnetic breakdown. The semi-classical approach is transparent and does not require large-scale numerical calculations of magnetic minibands. In order to explain the semi-classical approach, I will be using an example of 1.9 degree twisted double bilayer graphene. That is topologically a generic example for any system with a C3 rotational symmetry. Here I plot the valence band dispersion. For small hole doping, there are two small Fermi surfaces shown in blue. At some doping, a Lifshitz transition happens and Fermi surfaces merge, forming one new big complementary Fermi surface, shown in red color. In perpendicular magnetic field, equation of motion implies that real space trajectory will be a momentum space trajectory scaled by 1 over EB and rotated by 90 degrees. Away from the Lifshitz transition, at low hole doping, wave packets will be circling around small loops. At high doping, they will be circling in the opposite direction around a large complementary loop. Quantization of corresponding magnetic fluxes gives Landau levels and Shubnikov-de Haas oscillations as usual. But close to Lifshitz transition, quasi-particles can jump between the trajectories and hence evolve along an infinite network of trajectories. Quantum scattering between the nearby classical trajectories is called the magnetic breakdown. The quantum mechanical scattering amplitude to turn either left or right at the junction can be found from the exact quantum mechanical solution. On one side of the Lifshitz transition, it is higher probability to turn left, and on the other side of the Lifshitz transition, it is higher probability to turn right. As a result of magnetic breakdown, electrons can travel along an infinite chiral Kagome lattice of trajectories. To compute the conductivity, one may use the basis of the semi-classical wave packets in the Kubo type formula. Here the trace corresponds to integrating over arbitrary initial point. And we integrate over evolution time weighted with the probability to have no impurity scattering during that time. For finite scattering time, we can restrict calculation to finite size network, and the evolution operator becomes essentially a matrix in the space of Fermi surface segments. Product of evolution operator and its conjugate boils down to a probability to evolve from wave packet centered at in point to a wave packet centered at out point during time t. Consider elevated temperature where most oscillatory terms like Shubnikov-Dehas die out due to averaging over energy. But there are some oscillatory terms which surprisingly survive elevated temperatures. These come from equal duration interfering trajectories. The shortest possible of such trajectories are shown here in blue and green. The area between green and blue trajectories equals Brillouin zone area divided by EB squared and is hence independent of energy. So such contributions survive energy averaging due to finite temperature. The magnetic flux between the green and blue paths corresponds to Aharonov-Bohm interference phase and leads to Brown-Zak oscillations in evolution probability and correspondingly in the conductance. The shortest pair of interference trajectories gives the leading term because normally the coherence length is not large at elevated temperatures. The oscillating contribution contains both left and right turns when passing the saddle points. So it is non-zero only near the Lifshitz transition, where both turns are possible. Importantly, there is a different amount of left and right turns. So the corresponding amplitudes appear in a different power in the Seiden equation for conductance, namely power 6 and power 4. It means that the maximum of oscillation amplitude would be shifted from the position of the Lifshitz transition, as shown by green contour here. Accounting for energy broadening due to finite temperature leads to this formula for the amplitude of Brown-Zak oscillations. We see that it depends on the coherence length of the carriers, L, allowing to extract it from the experiment. Also, the maximum of amplitude of Brown-Zak oscillations is shifted from the Lifshitz transition doping by the amount proportional to magnetic field. So we arrive at theoretical predictions for the position of Brown-Zak amplitude maximum and full width at half maxima of the peak in Brown-Zak amplitude. Here, these predictions are matched to experimental results for twisted double bilayer graphene and for valence band of graphene on hexagonal boron nitride. In order to connect the semi-classical formalism to exact diagonalization approach, we consider a different limit of a very long coherence length. Then we take a large network and numerically compute, for example, the probability to return back to the initial point after some long time. The return probability at zero temperature is shown by blue and green curves and reflect a complicated Hofstadter butterfly spectrum. The return probability at elevated temperatures is shown by a red curve. It is non-zero for non-integer inverse flux, meaning a localization by magnetic field. For integer inverse flux, it vanishes, which corresponds to free ballistic propagation of Brown-Zak fermions away from the initial point. To summarize our findings, Brown-Zak oscillations are related to a class of Lifshitz transitions which produce an infinite two-dimensional network of Fermi contours. Semi-classical formalism supplemented with quantum magnetic breakdown amplitudes can be used to calculate conductance and explain the amplitude of oscillations. calculation is effectively reduced to a matrix model. Brown-Zak oscillations are a result of Aharonov-Bohm interference of equal duration paths in real space. In a lattice with C3 symmetry, a Lifshitz transition generically connects the phases with 1 and 2 Fermi surfaces. With increasing magnetic field, the position of the maximum of amplitude of Brown-Zak oscillations shifts from the Lifshitz transition point in the direction of one Fermi surface phase. Thank you for listening.